Okay, we continue on the equations related to the preloading. Okay. All right. Okay. So this is the equations. Okay. To determine the water flow. Okay, inside the preloading and vertical drain system. So let's say if we doesn't have any uh, vertical drain, okay, so then um, we rely on this equation to get the water flow uh, during the preloading process. Hmm. So what is CR is the coefficient of consolidation in horizontal direction. Okay, then we have a CV, coefficient of consolidation in vertical direction. So R is the radial distance. Okay. U is the pore water pressure at the distance of. Then this is the average pore water pressure. Okay. So since the consolidations is related to time, okay, so then T is the time. Okay. So that uh, is the equation, okay, to determine the pore water pressure or water flow, okay, of the water inside the um, soft soil area. Okay. Then this is a degree of consolidation. Okay. We need to identify what is the degree of consolidation, and usually we targeted to reach at least 80%, okay, uh, during the process of consolidation. Okay, U naught is the initial access for water pressure, and UT is the remaining access for water pressure at time of T. Okay. So from there, okay, we combine the degree of consolidation due to vertical and radial flow. If we have the preloading with the vertical drains, okay. So if we doesn't have the preloading, if we doesn't have the vertical drain, okay, so then doesn't need for us to use these methods. Okay, we just calculate the UV, okay, by using the UV equation. Okay, because UV and UR has their own separate equations. Okay. Okay, this is the equation for the UV. Okay. So to get the UV, we need to use these equations. Okay. So 1 minus 2 m 2 over m square exponent negative m square TV. Okay. So then what is m? M is the 2m plus 1 pi over 2, and TV is the time factor, which is CV times T over H square. So how to get the TV? Okay, we also can use this um, equation to relate with the UV. Okay, so this TV uh, is not a linear relationship. Okay, so it has two different equation based on the value on the time factor. Okay. Okay, let's say if the UV is less than 52.6, then we use this first equation. If it's greater than 52.6, then we use these TV equations. Okay. So that is for the UV. Okay. Now we look on the UR. Okay. So this equation we may use, okay, to determine the UR. Okay. Because okay, our our last aim, okay, is to get the UVR. Okay. So this is for the UV, and then this is for the UR. Okay. So F, what is F? Okay. So FND, okay, this is FND, the function of ND. Okay. So ND is the diameter ratio, which is the DE over DC. So what is DE? DE is the equivalent diameter of a unit cell. Okay. So what we learned here, okay, so this is the DE. Okay. Sorry, this is the DE. Okay. Means that this is the DE. While this is the DC. P. Yeah, okay. So, okay. So DC is the diameter of the sand grain. Okay. So T is the time factor due to the radial flow. Okay. Before this, the time factor based on the TV is the CV times T over his square. Okay. While for the radial is the CR T over DE square. Okay. So DE is the equivalent diameter of a unit cell. Okay. So then we solve this problem, solve this equation where ND is the FND, then TR, okay, is obtained. Where is TR? This is TR, okay, TR. Okay, this is TR. So then we obtain the degree of concentration due to radial flow. Okay. So average degree of concentration of a sand grain due to radial flow, considering smear and well resistance. Okay. So to include this issue of smear and wear resistance, so then we need to use the informations based on this diagram. For example, KS, okay? And this is lambda, okay? And also the smear diameter, ds, is equal to 1.5 to 3.0, the diameter of the sand grain or vertical drain. Okay, during the installations of vertical drain, the surrounding soil around the drain is often disturbed. Now that disturbed zone with a certain thickness is what we call as a smear zone, which has lower probability than the original soil. The diameter of the smear zone depends on the shape and size of the mandrel to install vertical drain and the type of sensitivity of the soil. So what is the mandrel? Okay. Let's see. There are no. Um, okay, let me find first the mandrel. Okay, during the installation, they have a mandrel, which is like a shoe. Okay, which is a rigid material, for example, from steel. Okay, to make it ease during the penetrations or and the installations of the uh, vertical drains. Okay, let me mandrel. All right. I'm not sure what's the problem. I just want to share the mandrel. Okay, so this is the example of the mandrel. Okay, why this is the mental shoe, okay? So then this is the PVD. Okay? So then due to these installations, okay, so mental section have overshipped. So okay? Due to this, this but then it cater for this disturbance, okay, as in the equation to include the low probability disturbance soil, okay, inside the full equation for the UV. Sorry, UR. Okay, so that is for the, okay. So then this is the proof. Then when we include the uh, smear and well resistance effect. Okay? The previous one does not include, okay, the issue from the Mandrel. Okay? So since they are very common to occur, okay, and also want to get a good prediction, so then the Mandrel uh, issue in the calculation for the UR. Okay? So then by including this issue, so the equation are a little bit lengthy compared to the previous equation without Mandel and smear effect. Okay, so diameter ratio of the smear zone to vertical drainage, diameter of smear zone, so it depends on the size of the Mandel. Radial probability of undisturbed surrounding soil, radial probability of smear soil, AS, Z, depth in the ground at which the degree of conservation is computed, HDR is the longest due to QC is the discharge capacity of vertical drain. Okay, so that is for the Mandrel effect on the UR calculations. So if we are using the vacuum preloading, okay, however, I do not have the example for the vacuum methods. Okay, so then this is the equation to determine the degree of consolidation, where US is the vacuum pressure at the depth of Z. Usually, the pressure applied is 80 kPa. Okay. UT is the pore water pressure at the depth Z and time t, and U naught is the initial pore water pressure at the depth of Z. So if US is equal to 0, the above equation can be used for the field preloading. So means that for the field preload, it doesn't, we do not have a UR as well. We only have a UV. So that is for the basic equations. Okay, later on we go for a very detailed to with the example. Okay. So surcharge preloading. Surcharge preloading apply a load higher than what is needed for a final load. Okay. To shorten the time required for preloading and minimize post-construction settlement, including the secondary settlements. Okay. So that is the use of the surcharge. After we have completed the pre-consolidation process, or the consolidation process, then we may remove the surcharge. Okay. In a technique of applying a high load higher than what is needed for a final load, mainly to shorten the time required for preloading and minimize post-construction settlement, including secondary settlement, surcharge preloading is often adopted in the practice. The extra load is removed after the completion of the preloading. This is the use of the surcharge. Okay, now we look on design considerations. Okay? So we have identified the basic equations for the preloading, for these preloading methods. So now we look on the design considerations. Okay? For the preload, for the vertical drain, preloading, and surcharge effect. Okay, so for the vertical drains, okay, the discussion will be on the type and patterns, equivalent diameter, capacity, probability, and optimal penetrations. Okay? So the equivalent vertical permeability is used in the Terzaghi dimensional consolidation solution to calculate the average drain concentration of vertical drains improved foundations. Okay. Okay, now we look and patterns. Okay. So this is the type and pattern of vertical drain that available in the markets. Okay, we have sand drain installation method, driven or vibratory closed-end mandrel, continuous auger, jetted, which is non-displacement method. Okay, the drain size are given there, drain diameter, typical spacing, and maximum time. So, wait a minute. Okay. Then we have a prefabricated sand drain. Okay. Driven or vibratory closed-ended membrane. Okay, flight auger in terms of installations, rotating wash boring, because we install the drain inside. We install a sand inside the or inside the hole. Okay, that's why we need to use a wash boring methods. Okay. So the diameter when there is 0.06, 0.15 with a typical spacing 1 to 4. Okay. And the maximum length is similar with the sand drain methods. Okay. So then we have a prefabricated band shaped drain or wick drain or strip drain. Okay, so this is made by the geopolymer, driven driven or vibratory close-ended mandrel, okay, displacement or small displacement. So then the diameter is 0.05 to 0.1 with a typical spacing of 1 to 3.5, and it can go up to 60 meter length. Okay. So the pattern type can be either square or triangular patterns. Okay. So then there are coefficients for the square and also coefficient for the triangular pattern. Okay, so then spacing are based on the typical spacing from this table. Okay. So then for coefficients to represent the equivalent diameter, okay, for DE is 1.13 times with the spacing for square patterns, while for triangular pattern is 1.06. Okay, where D is the equivalent diameter and S is spacing between two adjacent uh, vertical plane. Okay. So then equivalent diameter for PVD, okay, the equivalent diameter of PVD based on the perimeter equivalency and considering correction factor, okay, which is the DC. B is the width of the PVD, TG is the thickness of the PVD. Okay. The first one is related to the patterns, okay, while this is related to the diameter of the PVD. Okay. Alpha D is the correction factor. Okay. So TG is the thickness of the PVD. Okay. B is the width of the PVD. Okay. So then we have a discharge capacity. Okay, the discharge capacity to be considered as a free drain without any wear resistance. Okay. QC is 785 factor safety KR and HD square. Okay. So all these informations, later on we put either in the UR, okay. But for the DE, okay, DE, where is the DE? So this is the DS. Okay. So DE, you see there. This is DE, DC, 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 this is DC. Okay. Okay, this is the DE. So DC we include here. Okay. However, for DE, I need to find where is the use of the DE. Not here. Okay. That one where we should put the DE. Okay, so this is to get the DC. Okay, this is to get the QC. Okay. Or this is to get the probabilities and then we need to include the DE. Okay. So the equivalent vertical probability can be calculated using the following expressions and is used in Terzaghi one-dimensional consolidation solution to determine the average degree of consolidation of vertical drain improved foundations. Okay? So then we use this equation to determine the permeability. Okay? Let me find where we put the permeability. So that is for the KBE. Okay, 2.5 is the R divided with the FND DE KR over KV times KV. Okay, this is for the vacuum preloading to determine the optimum penetrations. Okay. For vacuum preloading, vacuum pressure often decrease with an increase of depth due to loss of vacuum. Okay. So when we want to determine the optimum depth for the vacuum suctions, okay, so then we use these equations, okay, which is the KV equivalent vertical probability minus KV1 is square root KV1 KV2 over KV1 minus KV2, where KV2 is the vertical probability of the soil below the PVD improved zone. So this is the KV2. So this is the KV1. Okay, from there, with the use of the vacuum, it's not necessary to penetrate up to the hard layer. Okay. So that is for the optimum penetrations. So now we look on the preloading. Okay? So that is for the PVD and also a little bit on the vacuum preloading. Okay. So now we look on the preloading. Okay. Allowable loads, loading, consolidation time, strengthening, degree of consolidation. From there, we can get the settlements. Okay. Okay. First, we need to calculate what is the allowable loads. Okay. So the allowable loads is the load where we determine from the capacity of the bearing for the soil. Okay. So from there we can get or know what is the limitations, okay, in order to make sure that there will be no foundation failure. Okay, for example, okay, we want to construct for the embankment. Okay, so we need to know how heights the embankment can be constructed. Okay, so how to know the capacity? Okay, we need to find first what is the bearing capacity, then divide the factor safety. Okay, so a rough calculation can be used to estimate the bearing capacity, ultimate bearing capacity. Okay, since we deal with soft soil, so the NC is equal to 5.14, then the NQ and N gamma usually either 1 or 0. Okay. But for this embankment, this rests at the top. Okay. So then there will be no value of the NQ. Okay. Sub-equations. Okay. Because in foundation, we have 3 sub-equations. The first one is the NC plus NQ plus N gamma. So this will be 0 if the phi is 0, if P is 0. So this will be 0 if the foundation rests on the ground surface. Okay. So then we obtain the NC, where the NC is equal to 5.14. Okay. So factor safety typically range from 1.1 to 1.5. Okay. So the preloading has mostly improved, okay, which is often normally unprotected. When these soils are subject to the field loading, they are more critical under undrained condition than under a drained conditions. So we need to evaluate the admissibility of the soft ground under a drained condition, which basically estimate the allowable pressure of a preloading. Okay. So the first task, we need to identify what is the capacity, okay, before we proceed for the next calculation. Okay. So for the preloading, okay, this is how we estimate the time, okay, from the preloading process. Okay, Taylor suggested a method to approximately the linear increasing load to an instantaneous uniform load starting from the middle of the loading periods. Okay. So in order to estimate the T1, okay, we use the T1 over 2 approach. Okay. So in the top loading, in practice, the load are often not applied instantaneously, but rather they are increased gradually. Okay. Because we apply one value, one thickness, okay, second thickness, third thickness until the desired heights. Okay. All right. So later on we will look on the example, okay, how to use this stage construction methods. Okay, so the times required for a desired degree of consolidation, okay, usually 80% in one stage can be estimated using the consolidation theory. For an instantaneous load, if no vertical drain is included, this equation can be estimated the time. Okay, so this is a common type of equation without having the vertical drains. Okay, so the time required for a desired degree of consolidation is 80%. One stage can be estimated using the consolidation theory discussed earlier. Okay. So a linear increasing load followed by constant load. Okay. Taylor and Olsen approach can be used. If vertical drain are included, the Hensbach solution of equivalent probability method by child is needed for calculation. When vertical drain are used, the portion of consolidation contributed by vertical flow is typically small, and the consolidation rate of 5 to 10% may be assumed for UV as starting point to estimate the required consolidation degree by radial flow. Okay, so if you have vertical drain, so then we can assume to use 5 to 10% of the UV. Okay, then later on we can estimate the required degree of consolidation by radial flow. Okay, we will discuss it based on the example later on. Okay, so that is for the consolidation time. Okay. So the undrained shear strength of a saturated corrosive soil can be estimated by using this equation. Okay. Once we have applied a preloading on the soil, then we want to determine again what will be the strength after the completion of the stage number 1 to be used during the stage number 2. Okay. So we need to calculate what is the strength gain after the stage 1 returns. Okay. Because we need to count for the bearing capacity with a new strength that gain from the preloading process. Okay. So then Cu over sigma Z time effective condensation stress is equal to SF, okay, times OCR powered by this letter. I'm not sure what this letter is. Okay, let me search first. What is the meaning of this letter? Greek letter. We open the Greek letter. Inverse B. Inverse B. Oh, there is no inverse B. Oh, they call it as a lambda. Okay. So inverse B is called as a lambda. Okay. So that is a lambda. This is lambda. What is the x? X is a chi. Okay. This is chi. Okay, this is chi. CHI. But this is lambda. Okay. Lambda. Chi and lambda. Okay. So this is the method to calculate for the strength gains. Okay. Okay, strength gain of the soil after consolidation can be estimated. Okay, delta Cu strength gains, delta sigma Z additional effective vertical stress induced by preloading, delta sigma Z additional total vertical stress induced by preloading, UT degree of consolidation at time T calculated by the previous step. Okay. T is equal to 0.25 for OCR1. So when the width of the load area is much larger than the thickness of the subsoil, okay, so then the delta Cu is equal to 0.25 degree of consolidation times P, okay, the total undrained shear strength after preloading, okay, can be used, it can be obtained as Cu1 plus Cu plus delta Cu. It depends on the, either you want to use case number 1 or the second case to determine the delta Cu. So that is for the strength gain. Okay, so this is for the what we call as a stage construction. So as we have discussed before, based on the Taylor, okay. So for these stage constructions, the example, okay, show 3 stage construction involved. Okay, for stage 1 at the time T1, okay, so means that we gradually load the soil, okay, until it completes the P1 pressure. Okay, so that is why the what we call why the pressure show a linear relationship with time. Okay, so once we have complete to the desired heights of pressure, then remain it for a several time. Okay, so at the stage 1, at time T1, so the degree of consolidations UT1 Pi under the loading P1 can be calculated by the time factor. Okay, so CV time T over H squared dr. Okay, so CV doesn't change. Okay, because that is the soil properties. But the time, okay, for the stage number 1 is the T1 here minus the T over 2. Okay. So then the equation has been simplified into CV T1 over 2H squared dr. Okay. So once we obtain this TV, we can estimate the UT. Okay. So the excess pore water pressure at the time is, okay, so to get the excess pore water pressure, okay, so then we may use the pore water pressure times with the height. Okay, later on we will look on the example. Okay, so the excess pore water pressure at the stage of 1, okay, is the initial excess pore water pressure times with 1 minus the time factor at the stage number 1, or degree of consolidation as the stage number 1. So it means that the excess pore water pressure has been reduced, okay, which is depend on the degree of consolidation. Okay? Where you note P1 is the initial excess pore water pressure induced by the instantaneous loading P1. Okay. So during the stage construction, each loading may not be held until the end of the primary consolidation due to the time constraint. Under such condition, some excess pore water pressure still remain in the soil from the previous loading when the next load is applied. As the result, excess pore water pressure accumulates from the previous loading period. Okay, so this is the initial excess. Okay, so means that it accumulates, okay, from the previous initial excess pore water pressure. So at 3-stage constructions, is selected as an example is illustrates the procedure on how to calculate the accumulated degree of consolidations. Okay. In this illustration, only the consolidation due to vertical flow is considered. Using the approximate method suggested by Taylor, however, this procedure also begins for consolidation due to radial flow. Okay? So we just focus based on the based on the preloading only. Okay? Okay. Not for this case include the vertical drain, but later on the example there is where you include the vertical drains in the with the preloading. Okay. Okay. At the time of T2, the degree of consolidation can be calculated at time factor CV at here, okay. This is T2, okay. So TV, okay, can be derived from T2 minus T2 over 2, okay. So that is the range of the time factor, okay, to get the degree of consolidations. Okay. So then the CV, okay, time 2T2 minus T1 over 2 H squared dr. Okay. So to get the excess pore water pressure, the excess pore water pressure at T2 here, before the next stage of loading is U naught P1 times 1 minus UT2 P1. Okay, then we get the UT2 P1. Okay. Okay. So that is for the stage number 1. Okay. Next, we start to increase the load, whereby it represents the T3. Okay. For stage 2, at time T3, there are two loading, okay, which is P1 and also P2, which have different time durations. Okay. So then the degree of consolidations under P1 and P2 minus P1, which is the UT3 P1 and UT3 P2 minus P1, can be calculated by the following time factor. Okay, so this is stage number 2. Okay. So at the stage number 2, there will be two time factor because actually we use the superimpose methods. Okay. So then a combination between stage 1 and stage 2. Okay. So for the stage TV P1 here, okay. So the equation involve CV T3 here minus T1 over 2. Then we obtain CV 2T3 minus T1 over 2 H squared dr. Okay. So that is for the TB3 P1. Then for the another TV3 P2 minus P1, okay. So then which is the T2 minus T3 over 2H square TR. So that is for the T3, P2 minus P1. Okay. Then for the pore water pressure or the excess pore water pressure under P1 is the U naught P1 times 1 minus UT3 P1, which is obtained from the TB3 P1, and the U naught P2 minus P1 times 1 minus UT3 P2 P1. Okay. So where U naught P2 P2 minus P1 is the initial excess pore water pressure induced by the additional instantaneous loading P2 and P1. So the accumulated degree of consolidation under P1 and P2 P1 at 3 can be calculated by these equations. Okay? So they combine between P and P2 minus P1. Okay. So at the time factor T4, which is the starting of the stage construction number 3, the degree of consolidations under P1 2 minus P1 before the stage of loading UT for P1 and UT P2 minus P1, okay, can be calculated by the following time factor: TV P1 equal to CV T4 minus T1 over 2 over H square dr. Okay. Then T4 P2 minus P1 is equal to CV 2T4 minus T2 minus T3 over 2 HD square dr. Okay, so that is for the T4. Okay, so the excess pore water pressure under P1 and P2 minus P1 at T4, okay, are given there. UT P1 equal to U naught P1 times 1 minus UT for P1. UT for P2 minus P1 equal to U naught P2 minus P1 times 1 minus UT for P2 minus P1. So that is for the excess pore water pressure. Okay. Why we need to consider excess pore water pressure? Okay, later on we may understand either the process of concentration is completed or not. If this pore water pressure is excess pore water pressure is equal to 0, so then we can say that the process of consolidation is almost completed. Okay. So the accumulated degree of consolidation under P1 and P2 P1 at T4 can be calculated as, okay, so this is the simplified equation. If the accumulated degree of consolidation for stage 3 or a later stage can be calculated following the same procedure as discussed above. Okay, so then we need to get until T5 and T6. Okay. So for this case, it looks like, okay, the author only completed at the T4. Okay. So then this is the power, access degree of consolidation, okay, for the UT4 T2. Okay. Okay, at the same time, we need to determine the settlement. Okay. The primary consolidation settlement at a certain time of preloading can be calculated by CC times H over 1 plus E naught log effective stress plus delta sigma Z over effective stress. That is for the C1. Okay. While for the SCT, settlement at time T are based on the degree of consolidation, UT, times with the SC. Okay, this is on the issue of the surcharge. So the effective surcharge ratio is defined as sigma ZS over sigma. Okay, sigma ZS here over sigma ZF. Okay, minus 1. Okay, then to ensure that the surcharge is relevant or not, so the surcharge usually should greater than the sigma ZF. That is very true. Okay. So to prevent the continued primary settlement after the surcharge, the achieved degree of consolidation should be equal to 80%. Okay. Okay. The UV or UTR should greater than the PF over PF plus PS. The primary rebound of the soil during and after the removal of surcharge, okay, from TRI to TRP here, TRI to TRP, okay, can be estimated by the following equations. CRH over 1 plus E naught log sigma ZF over sigma ZS. Okay. So since the sigma ZS is higher than sigma ZF, SR is negative rebound. The time of the end of primary rebound, PRP, and the rate of the rebound from TRI to RP can be estimated using consolidation theory with higher coefficient of consolidation due to a lower coefficient of volumetric probability. This primary rebound is followed by secondary rebound, which is typically small and can be negated for a conservative design in practice. Okay. So we also need to include, okay, if you use the surcharge, so what is the rebound value? Okay. All right. So now we go for the design parameter. Okay. Okay. So design parameter, what is the important parameter that need to be considered? Okay, the first one is the undrained shear strength, which is the CU, where we want to get the bearing capacity. Okay. Then we have a permeability, which is the K value, either KR or KV, okay, consolidation coefficients, okay, it depends on the type of the stress history. If for the over consolidation, so then we use the CR, which is the rebound coefficient. If normally consolidated, then we use the we use the CC, compressive coefficients. Okay. Initial port ratio, pre-consolidation pressure, okay, compressibility or compressions, compression or recompression index. Okay, so this is will be your CC and CR. Secondary compression index, C alpha, and the thickness of the soft soil. Okay, so that is the first parameter that we need to get. Okay. The second is the depth of groundwater table and drainage conditions. Okay, so we need to get the H. Okay, then we need to know what is the type of drainage. Okay, is it a double drainage or single drainage? Okay, what does it mean with double drainage? Okay, let's say this is your sand. Sorry, your topsoil, and if there is a sand on the top and at the bottom, so we can consider as a double drainage. If the situation that we have a pervious, impervious, okay, material, okay, where water is not allowed to move in that material, like fresh rock, or hard layer. So then we consider as a single drainage where water move to the top. Okay. Then we have a size of preloading area and intensity of preloading. Okay. Rate of loading, available time for preloading. Let's say if we may construct a new building, so we need to get what is the final structure load. Required factor safety, again bearing and slope failure. Okay? So then factor safety also need to be included. Okay. Preloading with vertical drain, the type of dimension, length, bearing capacity of vertical drains, pattern and spacing of vertical drains, size and probability of the smear zone. Okay. So then surcharge preloading, magnitude of the surcharge, time for maintaining surcharge, time for removing surcharge. Okay. So that is the important parameter that we need to prepare, okay, or get to calculate for the to use to calculate for the consolidation settlement. Okay. So then for the design procedure, okay, for the field preloading, okay. So what is the step? Okay. The first step is to estimate an allowable pressure based on the allowable bearing capacity of the foundation and the factor safety against slope failure if embankment are used for preloading. Okay. So get the CU, okay, then multiply with the 5.14 and divide with the factor safety. From there we can get what is the P value. Okay. If the allowable capacity is higher than the pressure, than the required pressure, so one stage loading is sufficient. Okay. Then the pressure is maintained until the end of the constructions. Okay. So once we calculate, then we found that the allowable capacity is higher than the required pressure. So only one stage loading is required. Okay. If the allowable capacity is less than the required final pressure, however, two or multiple stage construction, okay, is needed. Okay. So means that the capacity that can be sustained by the soil is less than the final pressure. Okay. So then we need to use the multi-stage loading. Okay. So calculate the rate of consolidation at the end of the preloading. If the degree of consolidation is less than the required vertical drains should be used and designed. Okay. Without having a vertical drain, we get what will be the rate of consolidation. Okay. So if the rate of consolidation is less, which is less than 80%, so then we need to use the vertical drain. Okay. So based on selected type, properties, pattern, and length of vertical drain, determine the spacing of the vertical drain. We have learned before, the equation involved. For the stage construction, strength gain is calculated under the previous pressure for a certain time period. The time period is often assumed at the consolidation of 80% and should be calculated first prior to determining the strength gains. Okay. So then we need to calculate what is the time periods, okay, where the rate should achieve 80%. Okay. All right. So then estimate a new allowable pressure based on the increased allowable bearing capacity. Okay. So it means that after we have applied the preloading, okay, for the first stage, so to go for the second stage, we have achieved an increment of strength of the material. Okay. So from there, we need to estimate again, okay, what is the new allowable pressure. Okay. If the new allowable pressure is capacity is higher, then the required pressure, the remaining pressure is in the addition to the previous pressure is applied and maintained until the end of the construction with a settlement calculations. So it means that it doesn't require for us to have an additional preloading. Means that will be enough to only. So otherwise, repeat step 2 and 3 and 4 until all the required load are applied. If not, we need to have additional stage loading after that. Okay. Calculate the accumulated degree of consolidation based on the accumulated excess pore water pressure from each stage of loading and the dissipation of excess pore water pressure during preloading. Calculate the settlement of the foundation for each corresponding stage. Then calculate the post-construction settlement, including secondary compressions. Okay. So then, after we have complete for the construction stage calculation for the settlement, especially for the primary consolidation, then we also need to estimate what is the post-construction settlement after the structure has been used by the public. Okay, so it's more related to estimate the settlement post-construction settlement. Okay, so how to get the value? Okay, we need to use the secondary compression equations. Okay, so based from the local authority, especially in Malaysia, okay, so the post-construction settlement, okay, after 5 years, okay, should not be more than 250 meter. Okay, so we need to monitor, okay, what is the settlement, okay, after the post-construction of the geotechnical structure. For example, if we construct for embankment, okay, then we need to measure what is the load, what is the settlement, okay, occur after we have after it's been open to the public, okay, for 5 years, for example. Then compare with our estimations, okay, and it should not greater than 250 millimeter. Okay. So if surcharge periodic is used, okay, the reduced secondary consolidation index can be determined, okay, using the Ladd method or the Mesri et al. Method. Okay. Okay, for the secondary compressions, okay, the use of the C alpha, okay, to estimate the secondary compressions. Okay. There is a chart, okay, from Ladd, okay, from Mesri, okay, to estimate what will be the C alpha value, okay, based on the loads applied. Okay, so from there we can estimate the secondary consolidations. Okay. Okay. All right. Okay. I just completed on the explanations for the preloading, vertical drains, and the vacuum. Okay. So we take a rest, okay, before we continue for the example. Okay. We go first with the simple one. Okay. which is I give it this morning. Then we go for the stage constructions. Okay, I will give another. I will share the same with the stage construction example that actually I take it from a reference book. Okay, so that will be more uh, clean to be understand. Okay? So we take a break for 15 minutes. Okay, so we meet at 11:30. Okay. Okay, we meet at 11:30. Okay.